Good afternoon. This will be the last lesson on 5.2 on the maximum problems in the standard form using the simplex algorithm. As I mentioned before, there will be one more lecture on solving the minimum problems in the standard form, and we will skip then the non-standard form, and that'll be it for chapter 5. So in this section, I just want to go over two more examples and give you some other little tricks of the trade, so to speak. My first goal for today is to give you an example when the maximum problem doesn't have any solution. If you remember, if you get into the position in which you need to pivot, meaning that there are still negative entries in the objective row, and you can't choose a pivot because all the entries in the column of the pivot are negative, that means the problem doesn't have any solution. So I think it's useful to look at an example in the two variables so that you can see graphically why that actually is possible, why it's possible to have no maximum. And the idea is that actually you can actually end up with arbitrarily high value for the objective function. So in that sense, the maximum doesn't exist. There is no the highest value of p. So here's an example. So suppose the constraints, so suppose the problem is to maximize p equals, let's see, x plus y. Let's choose easy entries, coefficients equal to 1 as much as possible. Maximize p equals x plus y subject to the constraints x minus y less than or equal to 1, 2x minus y less than or equal to 3, x positive, y positive. So let's go a little bit faster now because you should get used to the process by this point. So we change these constraints into a system of equations using the slack variables. 2x minus y plus s2 equals 3. And remember, we move the x and y to the left side of the objective function. So with this system, we proceed to set up the initial simplex tableau. But before we do that, let me actually illustrate how the feasible domain looks like. So if you were to graph, as you know from previous sections, if you were to graph this system of inequalities, because we could do that in two variables, you should actually try to do this on your own. Maybe pause for 5 minutes, pause the video and take 5 minutes or so to do it on your own. Just to save time, I'm gonna just give you the domain, the feasible domain for free, so to speak. So one line goes to the points 1, 0, 0, minus 1, the first constraint, and the domain, the first inequality is going to be above this line. So let's say this is 1, this is minus 1. So that's the line that corresponds to the first inequality. Basically, x minus y equals 1. And then the other one goes to the points, let's see, minus 3. If x is 0 is minus 3, which is further down here. That's one of the points. And the other one is, let's see, if y is 0, y would be, if y is 0, x will be 3 over 2, which is a little bit further to the right here. So that's another possible point of that second line. All right. If you use the origin as a test point, it's not hard to see that the feasible region is going to be above these two lines. And I'm not going to compute the corners now because I'm going to use the simplex algorithm anyway. But again, together with the positivity condition that x is positive and y is positive, the feasible domain for this problem is this region that I'm going to emphasize right now. Let's see if I can do that in a suggestive manner, so to speak. So I want you to notice that this feasible region is no longer a closed region. So it's not closed. It opens up indefinitely. And so that means we know already why the maximum doesn't exist. If you look at the objective function over here, p equals x plus y, right? you can actually plug in arbitrarily high numbers for x and y, because you can go up in this region as far as you want. And by going up in that feasible region, you can pick any value for x and y, any positive value for x and y, no matter how big. So there won't be a maximum for this function. So let's see how the simplex algorithm basically tells you that. Right? Because remember, if you have more than two variables, we can't do this analysis using the graphical method, right? We can't exactly sketch the feasible region if we have three or more variables. So let's go back to the system on the right hand side here and set up the initial simplex tableau. Again, remember, starting with the basic variables, the columns for p, x, y, slack variables on the right hand side. I hope you know the drill so far. Already. So the column for p will be 0, 0, 1. For x will be 1, 2, and minus 1. For y is going to be minus 1, minus 1, minus 1. Then the slack variables 1, 0, 0, 0, 1, 0. And of course the right hand side 1, 3, and 0. Basic variables to begin with are S1, S2, and P. So what about the pivoting? So remember, we look for the first non-zero and first negative entry on the P row, which is the first minus 1. Then we look at the positive ratios between the right hand side and the pivot column. So you look at 3 over 2, 1 over 1. This is the least ratio, which means the first pivot is going to be that entry equal to 1. It is already 1. We don't have to divide that row by anything, so we just make zeros below that pivot. So we're going to do, on the next step, we're going to do minus row 1 times 2 plus row 2, and we change row 2, and then we simply add row 1 to row 3 and change row 3. All right, so the tableau becomes, let's copy the first row, 0, 1, minus 1, 1, 0, 1. Let's see. Then the next row, minus 2, row 1 plus row 2. So it's going to be 0, 0. Minus 1 times minus 2 becomes 2. Minus 1 is 1. Minus 2 times 1 plus 0. Minus 2 times 0 plus 1. Minus 2 times 1 plus 3 is 1. Add row 1 to row 3. 0 plus 1. 1 minus 1. Minus 1 minus 1 becomes minus 2. 1 plus 0. 0 plus 0. And 1. Let's double check. All good. 1, 0, minus 2, 1, 0. So the last one is going to be the P row. When you are at this, remember, if you are on these intermediate stages, you don't have to write all the labels if you still have to pivot. You're going to write all the labels at the end when you have to extract the solution, if any. Right now, what you have to notice is that as long as we still have negative entries in the last row, we still need to pivot. When you look at the ratios, right, so this is the right hand side, so maybe actually we should probably, let's actually do the labeling just to emphasize that when you look at the ratios to choose the pivot row, obviously look at the ratios between the right hand side and the pivot column, but only the positive ratios. So for example, no ratio is to be evaluated on that row, right? Because on the first row, because you have 1 over minus 1, remember, you ignore all the negative entries or all the negative ratios. So remember, ignore negative ratios when you choose the pivot. So the only possibility for the pivot is this one. Again, we don't have to divide this row by the pivot because it's already 1. All we got to do is to make zeros above and below that pivot. So we're going to do row 2 plus row 1 and change row 1 with that combination, and 2 row 2 plus row 3 and change row 3 with the same combination. All right, so the simplex tableau, again, let's write the labels. We won't need them, but just to keep track as before. So row 2 plus row 1 is going to be 0, 0 plus 1, 1 minus 1, minus 2 plus 1 is minus 1, 1 plus 0, 1 plus 1 is 2. Copy the pivot row. And then the last row becomes 2 times row 2 plus row 3. 2 times 0 plus 1. This is again 0. 2 times 1 plus minus 3 is 0. 2 times minus 3 is minus 4 plus 1 is minus 3. And then 2 times 1 plus 0 is 2. 2 times 1 plus 1 is 3. All right, so just for practice, if you want to look at the basic variables, now these are in this order: x, y, and again p is also a basic variable. Okay, so here is the key moment, right? As you move from left to right, you still have a negative entry. So this will be basically the pivot column. You still need to pivot since you have a negative entry. But now there is no negative ratio when you have to choose the pivot row, right? If you look at the pivot column, let's emphasize it here, you only have negative ratios: 3 over minus 3, 1 over minus 2, 2 over minus 1. So when you have to pivot and you can't choose a pivot, so must pivot, because we still have negative entries on the last row, but can't choose a pivot because of the negative entries on the column of the pivot. So this is basically the stopping criteria in the simplex algorithm, that there are no solutions, or no solution, because you're looking for the maximum of p. So the objective function doesn't have a maximum in this case. So remember, 2 stopping criteria for the algorithm. You end up with positive entries on the p row, you reach the maximum. You end up with with at least a negative entry on the p row, but you can't choose a pivot because all the entries on the top above it are negative. That means there are no solutions. So we're going to move on to the second page, and we're going to do another example. But on that example, I'd like to show you something which is not mandatory. I mean, only if you prefer a slightly different way to pivot, which kind of reduces the number of intermediate steps sometimes. And you might prefer it to use it alternatively with the way I taught you so far to pivot. So stay tuned for the second part, or the second page of this lecture. So what's this another way to pivot that I'm talking about? It's basically a way to make it in one step rather than two. Because remember, the usual way involves an intermediate simplex tableau. So that means divide pivot row by pivot, and then you write the tableau, and then the second part will be to create zeros above and below the pivot. But here's a way to actually rewrite the whole table in one step. And so let's write schematically. Imagine, for example, you are at this stage in which you have in a given row the actual pivot. So let's circle it and call it P. The entry above it, let's call it A, and somewhere to the right and to the left actually doesn't matter. I'll show you actually with both, in both cases. Let's say B, an entry is further to the right. Let's say you have an entry here, C. Let's say this is D, and this is E. What are these two operations do actually to these entries? Well, for once, you still do this step. I mean, you still divide the pivot row by the pivot. Okay, which means basically D will be D over P you know, E becomes E over P, and of course P becomes 1, right? P over P, which is 1. This is still what you do, but you could do the other entries at the same step. So that's my point here. You don't need to rewrite the whole table to update the other entries outside the pivot row. For once, anything above or below the pivot is going to be 0, will become 0 basically. So you can basically replace A with 0 right away, right? I mean, you can, or also anything below the pivot as well. The real question is, how do I update the other entries on the other rows which are not on the pivot columns? Well, look what happens here. If I actually divide by the pivot and then create 0 to, I mean, how do I make A to be 0? How does that happen, right? The fact that A becomes 0. Well, that happens in the following way. Once you divide the row, the pivot row by P, you're going to multiply the pivot row by minus A to make it 0 above it. So the pivot row will be multiplied by minus A and then added to the row above. But my question was, what is that, or my observation is, what does that mean for the other entries for B? Well, B will change in the following way. The entry below it is going to be D over P, because remember, you first divided by the pivot, and then you multiply that by minus A later, because that's what you do with that row to make 0 above the pivot. And then you're going to add that to the row above, so you're going to add it to B. So B changes in that fashion. D over P, because you divide the row by the pivot, and then minus A times minus A, because you make 0 above the pivot, and then you add it to B. But if I actually rewrite a little bit differently this fraction here, I'm sorry, this expression as a single fraction, and let's write the common denominator. So I'm going to multiply B by P on top, on the bottom. This is going to be B times P minus AD over P. So B becomes B times P minus AD over P. And you can memorize this pivoting way, I mean this alternative way to pivot, by thinking in terms of creating some sort of rectangle between the entry that you want to update, B in this case, and diagonal to P, and then the other corners of the rectangles, which are A and D. So you can think of B being replaced as the difference or cross product, if you want. So B times P first minus A times D. So you form that rectangle, and that's going to be the new value of B. It may sound a little bit complicated, but if you practice with this a little bit, you might actually like it. And with C, you do the same thing. You always form a rectangle. So the same thing works for any entry to the left of B. You form a rectangle, and then C becomes C times P minus A times E over P. And same thing for the entries below the pivot. You don't have to sketch these arrows on the paper. The idea is to do them in your mind. But as I said, with a little practice, if you prefer, you could do that. If you find it uncomfortable, by all means, forget about it. Just I put it here for anybody who wants to use it. And just use it in 2 stages, like we did it before. You know, the division by the pivot first, and then the zeros below and above. In practice, I like to actually use both methods depending on how the pivot looks like. And I'm going to illustrate with an example just to see what I'm talking about. Let's start with a simplex tableau right away to save some time. So basic variables. This will be a simplex tableau with actually 4 variables. So you have the objective variable x1, x2, x3, x4, but only 2 constraints. So we're going to have just, I should have put the bar here. We're going to have just 2 slack variables. So 0, 0, 1, obviously the first one, 2, 4, minus 1. 4, 4 and minus 2, 5, 2 and 1, 6, 2, and minus 3. 1, 0, 0, 0, 1, 0. And the right hand side in this problem is 24, 4, and 0. Make sure you pause the video and catch up. Take your time. Don't rush. I mean, I always count on you guys to actually pause the video if necessary. So, because there's no point for me to slow down and make the video too long. I mean, unnecessarily long, since you guys have the pause button at your disposal. So, obviously, when you choose the first pivot, that's the first pivot column. Let's look at the ratios. 4 over 4, 24 over 2. The least ratio corresponds to this 4. This is a typical example in which the alternative pivoting method will be preferable if you want. Because then if I divide by 4 and then create zeros, I'm going to have to deal with fractions. Maybe it's not that easy. Or more comfortable to use this. But pay attention how the rectangles are formed. So when you write the new table, you kind of have to start basically with, you're going to have to remember that on the column of the pivot, you're going to place zeros above and below the pivot, and then the pivot becomes 1 since you're going to divide the second row by 4. But all the other entries will follow this trick with the rectangle. So for example, the entry 0 here is going to still be 0 because it's 0 times 4 minus 0 times 2 over 4. So this is going to be still 0. The next one is on the pivot column, so that's going to be 0 for sure. Now pay attention here, I'm going to do the scratch paper on the right. I'm looking to update this 4. So with the alternative pivoting method, it's going to be 4 times 4, you go on the diagonal, minus 2 times 4 divided by the pivot. So that's 16 minus 8 over 4, 8 over 4, that's 2. So the next entry is 2. Now I look at 5, again form the diagonal with the pivot, 5 times 4 minus 2 times 2 over 4, 20 minus 4 makes it 16 over 4, that's going to be 4. We're looking now at 6, diagonal, 6 times 4 minus 2 times 2, divided by 4, 24 minus 4 over 4, 20 over 4, that's 5. Let's do this mentally for 1. 1 times 4 is 4, minus 0 over 4, that's going to be 1. I think, let's see, 0, 0, 2, 4, 5, 1. Okay. We're looking now at this 0. 0 times 4 minus 2 over 4. So 0 times 4 minus 2 times 1 over 4. That's going to be minus 1/2. Finally, the right-hand side, 24 times 4 minus 4 times 2 divided by 4. Let's see, this is going to be 24 minus 2, 22. Is that right? Yes, 22. Pivot row, remember, is divided by 4 by the pivot. 0, 1, 1, 2 over 4 is 1/2. Another 2 over 4 is another 1/2. 0 over 4, 1 over 4, 4 over 4, which is 1. And then we form again the diagonal. So 1 times 4 minus 0 over 4, that's going to be 1. Underneath the pivot, remember, that's going to be 0, right? The pivot column is 0 except the pivot. Here we have to pay attention to some obvious negatives here. So we're updating this one on the last row. So you're going to do 1 times 4 minus 1 times 2 over 4. That's 4 plus 2, 6 over 4, which is 3 over 2. So 1, 0. Let's see. I think I skipped one, didn't I? I skipped the minus 2. Sorry about that. So the one before. This is still, like I said, 3 over 2. But I skipped the one before it. Minus 2 times 4 is minus 8. Minus negative 4 makes it plus 4. So minus 8 plus 4, that's minus 4. Divided by 4, that's minus 1. Moving on, minus 3 times 4 minus negative 2 divided by 4 minus 12 plus 2 over 4 minus 10 over 4, which can be simplified to minus 5 over 2. The next one is easy. 0 times 4 minus 0. Then 0 times 4 minus negative 2 over 4. That makes it, let's see, minus 5 over 2, 0. 0 times 4, yeah, I mean the diagonal is 0 times 4 with 1 and minus 1. So you're looking at, let me actually make a mess a little bit just to see. When you look at this 0, you form the rectangle 0 times 4 minus negative 1, which makes it 1 divided by 4, that's 1 over 4. So you form a rectangle diagonally with the pivot. And finally the last entry, 0 times 4 minus negative 4 over 4, which is 1. So I don't know if I'm going to finish this, but again, if you like, go slow and go over this alternative pivoting if you like to. This is actually a slightly longer problem. We're not going to finish it. Well, let's see. The next pivot is going to be this one. 1 over 1, 22 over 2. Let me just give you the next tableaus, and I'll leave you as an exercise to check with whatever pivoting method you want to do. Check yourself to see that you get these values. So the next tableau should be 0, minus 2, 0, 3, 4, 1, minus 1, 20. I wonder how many of you actually are going to do the exercise. I know there are some of you who know, who do what they're supposed to do, but the opposite is also true. Just remember, this is not me punishing, it's just practice. I mean, love it or hate it, math requires practice, and it's as simple as that. And if you have to take this class, you might as well practice, and practice some more. Now, on the last row, we still have a negative value. If you look at the ratios, 1 over 1/2 is 2. 20 over 4 is 5, so now the new pivot is 1/2. Do the work slowly, and the last the next one will be the last tableau. It should be 0, minus 10, minus 8, minus 1, 0, 1, minus 3, 12, 0, 2, 2, 1, 1, 0, 1/2, 2, and then finally 1, 5, 4, 4, 0, 0, 3 over 2, and 6. So the algorithm stops right here because the last row will have only positive values. And remember, let me see if I can squeeze them here. The variables are p, x1, x2, x3, x4, x5, excuse me, these are slack variables, S1, S2, and the right hand side. It's kind of a mess here. Sorry about that. I just want to point out the basic variables at the end. S1 is the first basic variable corresponding to 1, 0, 0. X4 is the second basic variable, and as usual, P is also a basic variable. So the maximum for this problem is P equals 6, and it is attained for X4 equals 2, because X4 is a basic variable, and all the other variables are 0, because they're not basic variables. Anyway, the point was not so much to finish this problem, but to illustrate this alternative way of pivoting if you prefer to use it. Now, to anticipate, the last lesson of chapter 5 will be a little bit easier in the sense that, because we're going to deal with the minimum problem in standard form. To solve the minimum problem, one essentially makes a little change, a transpose in a matrix, in a special matrix I'm going to show you, and change the minimum problem into a maximum problem. So basically, you still do the same thing what you did in 5.2, but with an additional step in the beginning, which is designed to change the minimum problem into a maximum problem in standard form. And that'll be the last topic on the simplex algorithm. So that's it for today. make sure you watch everything by the exam time. And obviously you did that if you get to this point, because that's the last lesson before exam. See you later.